One of the most profound questions people regularly pose to me concerns whether the universe is infinite. It's a deceptively simple inquiry that leads into some of the deepest uncertainties in modern physics. The honest answer is that we don't yet possess enough information to give a definitive response. Our understanding depends critically on two unknowns: the total quantity of matter distributed throughout the cosmos and the precise strength of gravitational forces across vast distances. However, what makes this question so compelling is that we do understand quite a bit about what the mathematics tells us, and the potential answers prove far more extraordinary and counterintuitive than most people imagine. At this very moment, space itself is undergoing expansion. The universe is growing larger with each passing second. Distant galaxies, situated billions of light years away from our vantage point, are rushing away from us at extraordinary velocities measured in thousands of miles per second. This phenomenon isn't random or chaotic. It follows a consistent mathematical relationship. The critical factor is distance. The farther away a galaxy happens to be, the more rapidly it moves away from us. The fabric of space between all these galaxies continuously stretches, expands, and grows. Every single second, the universe becomes larger. We don't experience this expansion directly in our daily lives because the effect at our scale is negligible, yet the phenomenon is genuine and measurable. This ongoing expansion carries profound implications when we contemplate cosmic history. If we reverse time in our minds and trace the universe backward, we arrive at a logical conclusion. The outward motion we observe today means everything was closer together in the past. Running this thought experiment further backward, we can imagine galaxies progressively compressing into smaller regions of space, becoming increasingly dense and hotter. Continuing this regression further back in time, we eventually reach a state where every galaxy, every star, every atom, and every particle of matter was compressed into a single infinitesimal point of unimaginable density and temperature. This primordial moment represents what we call the Big Bang. It's essential to understand that this wasn't an explosion occurring within space. Rather, it was the explosion of space itself, the very moment when space, time, and all existence began. The story of how we discovered and understood this cosmic reality begins in the 1920s, when astronomers started systematically examining distant galaxies and analyzing their light. They made a puzzling observation that contradicted their expectations. The light arriving from these distant objects wasn't displaying the colors and wavelengths they predicted. Instead, the light showed a consistent shift toward the red end of the electromagnetic spectrum, a phenomenon termed redshift. At first glance, this might seem inconsequential. After all, light changes color in various ways throughout the universe. But what captured the astronomers' attention was the pattern they discovered. There wasn't randomness in these observations. Instead, they found a clear mathematical relationship. Galaxies situated at greater distances exhibited more pronounced redshift. This wasn't a minor effect either. The shift was substantial and consistent. The physics behind this observation relates to motion and wave behavior. When objects move away from us, the light they emit gets stretched, similar to how the pitch of a car's siren drops as it drives away from you. This acoustic phenomenon has a direct parallel in light waves. When a light source moves away from an observer, the wavelengths of the light extend, stretching toward the red end of the spectrum, hence the term redshift. The greater the recession velocity, the more pronounced the effect. So the observations from the 1920s provided strong evidence for an expanding universe, with galaxies moving apart from one another due to the expansion of space itself. This revelation leads naturally to the next critical question. What is the ultimate fate of this expansion? Will the universe expand indefinitely, or will something eventually reverse this trend? The answer hinges entirely on a single dominant force: gravity. Every object in the universe, from the smallest particle to the largest galaxy cluster, possesses mass, and mass generates gravitational attraction. Gravity fundamentally acts as a pulling force, drawing objects toward one another. Even though space itself is expanding and carrying galaxies apart, gravity simultaneously works against this expansion, attempting to pull everything back together. This tension between expansion and gravity creates a cosmic drama with multiple possible endings. Consider an analogy from everyday physics, throwing a ball upward against Earth's gravitational field. What happens depends on the initial velocity. Throw the ball slowly, and gravity quickly dominates. The ball rises briefly, its velocity decreases, it stops momentarily, and then falls back to the ground. Throw the ball faster, approaching what physicists call escape velocity, and a different outcome emerges. The ball rises higher and higher, its upward velocity continuously decreasing but never quite reaching zero. Mathematically, the ball would continue rising forever, with its velocity asymptotically approaching zero. Throw the ball faster still, exceeding escape velocity, and it escapes Earth's gravitational influence entirely, rising indefinitely while maintaining some residual velocity. The universe follows this same logical framework. The outcome depends entirely on the balance between two competing factors: the rate at which space is expanding and the strength with which gravity opposes that expansion. This balance yields three mathematically distinct scenarios, each representing a different cosmic destiny. In the first scenario, space expands at a velocity that overwhelms gravity's restraining influence. Gravity proves insufficient to slow the expansion meaningfully. In this case, the universe expands forever, with galaxies continuously racing apart and increasing their separation distances. Over cosmic timescales, galaxies eventually become so distant from one another that light from one galaxy cannot possibly reach another. Each galaxy becomes isolated in complete darkness. Stars within these galaxies gradually exhaust their fuel and burn out. The universe enters a state of ever-increasing cold and darkness. Eventually, the universe reaches a condition where nothing interesting can ever occur again, a heat death where all meaningful activity ceases, and eternity becomes an unchanging, empty void. The second possibility presents a different but ultimately similar fate. In this scenario, space expands at precisely the critical rate where gravity's pull exactly matches the expansion's push. The universe remains balanced on this knife's edge, expanding perpetually but with continuously decreasing velocity. At infinity, in the infinitely distant future, the expansion rate approaches zero, but expansion never fully stops. This represents the mathematically flat universe. While the mechanism differs slightly from the first scenario, the ultimate outcome is essentially identical: endless expansion, increasingly cold temperatures, and an eventual state of maximal darkness and entropy. The third possibility stands in stark contrast, offering a dramatically different fate. In this scenario, space doesn't expand quickly enough to overcome gravity's overwhelming strength. Gravity, being too powerful, gradually slows the expansion. First, the rate of expansion decreases, then expansion completely stops. Finally, the process reverses. Galaxies cease their recession and begin approaching one another. Space itself begins contracting, becoming denser and hotter. To understand this state, imagine the Big Bang running in reverse, a process sometimes termed the Big Crunch. As space contracts, galaxies collide and merge with one another. The incredible gravitational forces tear stars apart into their constituent parts. Matter becomes increasingly compressed and temperatures rise dramatically. As this contraction accelerates, the universe returns to increasingly extreme states. Atoms can no longer exist in such heat and pressure. Molecules disintegrate. Even subatomic particles cease to maintain their structure. Eventually, all the matter and energy in the entire universe compress back into a single infinitesimal point, a singularity. Whether this leads to another Big Bang, some other exotic state, or something entirely beyond our current understanding remains unknown. We cannot yet definitively say which of these three fates awaits our universe. The answer depends on the total quantity of matter throughout the cosmos, not just the visible matter we can observe through telescopes such as stars, planets, and galaxies, but all matter, including vast quantities of invisible matter that doesn't interact with light but does exert gravitational effects. Until we fully understand this matter distribution and measure gravity's strength across cosmic distances with greater precision, we cannot determine our universe's ultimate destination. While contemplating this grand cosmic question, I found myself wondering about a related phenomenon at smaller scales. If the entire universe can potentially collapse under its own gravity, what about individual stars? How do smaller objects behave under similar gravitational pressures? stars provide fascinating case studies for gravitational collapse. Most stars remain remarkably stable for enormous timescales, millions, billions, even hundreds of billions of years. This stability results from a delicate balance of forces. Within a star's core, nuclear fusion reactions occur, releasing tremendous energy. This energy, in the form of radiation pressure, pushes outward with considerable force. This outward pressure perfectly balances the inward crushing force of gravity, creating an equilibrium that permits the star's stability. However, nothing endures forever. Stars eventually deplete their fuel reserves. The hydrogen that powers stellar fusion through nuclear reactions becomes exhausted. Fusion processes slow and eventually cease entirely. Once the outward pressure from radiation disappears, gravity becomes unopposed and rapidly dominates. For smaller stars comparable to our Sun, this process unfolds relatively gently compared to more massive objects. The star gradually cools and contracts. Its structure transforms into what astronomers call a white dwarf, an Earth-sized remnant composed of incredibly dense matter. Although initially quite hot, this stellar corpse slowly radiates its remaining heat into space over incredibly long timescales measured in trillions of years. Eventually, the white dwarf cools completely, becoming a cold, dark, essentially dead sphere, a stellar relic persisting in the universe long after it ceases any meaningful activity. For massive stars, substantially more massive than our Sun, the death process differs dramatically. Instead of the gentle cooling and contraction experienced by lower mass stars, massive stars undergo violent, catastrophic collapse when their fusion ceases. The core collapses with such rapidity and force that the process completes in mere seconds. The immense gravitational pressure forces electrons into protons, combining them to form neutrons. The entire core transforms into neutron matter, a substance composed almost entirely of neutrons packed together with absolutely staggering density. The resulting object, called a neutron star, possesses extraordinary properties. Despite containing a mass comparable to our Sun, this neutron star has been compressed to only the size of a city, perhaps 30 kilometers across. The density exceeds all common comprehension. A teaspoon of neutron star material would weigh as much as an entire mountain or larger. Gravity at a neutron star's surface reaches such extreme intensities that if you dropped an object from merely 1 meter above the surface, it would impact the surface at a velocity equivalent to a significant fraction of light speed. Despite their extreme density and gravitational intensity, neutron stars cannot grow indefinitely massive. Physical limits constrain how much mass a neutron star can support through the quantum pressure of its matter. Specifically, the Chandrasekhar limit, named after the physicist who calculated it, sets a boundary at approximately 1.5 times the Sun's mass. Push beyond this limit, adding more mass to a neutron star, and the internal pressure cannot support the additional weight. The neutron pressure that holds the star intact becomes insufficient. The collapse continues inexorably, and here is where the physics becomes truly strange and exotic. I began examining the mathematics underlying gravity near extremely massive, dense objects with careful attention. These equations, Einstein's field equations from general relativity, describe how gravity functions and how space and time behave near massive objects. For ordinary objects like planets, stars, and even neutron stars, these equations function perfectly well. They successfully predict gravitational behavior, how time flows, and how space curves. But something remarkable emerges when matter reaches sufficient density. The mathematics predicts a critical boundary, a special size associated with any given mass. Below this size, the equations describe something genuinely bizarre. The math predicts a point where time itself stops flowing, where space curves back upon itself completely, creating a boundary from which nothing can escape. This special size is called the Schwarzschild radius, named after Karl Schwarzschild, who discovered this solution to Einstein's equations in 1916. The Schwarzschild radius varies with mass. For the Sun, this critical size equals approximately 3 kilometers. For Earth, the Schwarzschild radius measures only about 9 millimeters, the size of a marble. For any object, simple calculations using mass alone can determine the Schwarzschild radius. More massive objects have larger critical radii. However, the Schwarzschild radius grows more slowly than the actual radius of ordinary objects. Consequently, normal objects like stars and planets are nowhere near their critical size limit. Their actual physical size vastly exceeds their Schwarzschild radius, so these boundaries remain purely theoretical for everyday objects. But imagine a thought experiment. Suppose somehow you could compress the sun into a 3-kilometer sphere, or compress Earth to marble size. You would breach this critical boundary, the Schwarzschild radius. At that boundary, something profoundly strange occurs. An object compressed below its Schwarzschild radius becomes what we called a collapsed star in the 1960s. Some colleagues called it a frozen star for reasons that will become apparent, while others use the term black star because of the fundamental property that light cannot escape from such an object. Regardless of terminology, the predictions emerging from the mathematics are genuinely bizarre and counterintuitive. Consider a vivid thought experiment illustrating what happens to someone falling into such a collapsed star. Imagine a massive star actively collapsing. Its core implodes catastrophically. Gravity crushes the star into ever smaller dimensions. Picture an observer standing on the star's surface, riding it downward, falling inward with the collapsing matter itself. Simultaneously, imagine you positioned safely far away from this drama, observing the events through a telescope. What would you witness? Initially, nothing appears particularly remarkable. The star shrinks progressively, becoming denser and more compact. The observer on the surface falls inward along with the stellar material. Light from the star's surface travels across space to your telescope, allowing you to watch the observer. Perhaps he signals to you, waves, or sends light signals to communicate. But as the star approaches its critical size, its Schwarzschild radius, genuinely strange phenomena begin occurring. The light reaching your telescope from the surface changes character. It grows progressively redder and dimmer. This represents gravitational redshift. Light climbing out of an intense gravitational field loses energy in the process. The light waves stretch, shifting toward the red end of the spectrum. The stronger the gravitational field, the more pronounced this redshift becomes. As the star approaches its critical radius, gravitational redshift becomes extreme, and the light grows increasingly difficult to detect. Simultaneously, something stranger occurs. Time itself becomes affected by the intense gravity. From your distant perspective, the observer's movements appear to decelerate. If he waves his arm, the motion seems to take longer than it should. His actions slow down progressively. From his own perspective, nothing unusual is happening. He waves his arm at normal speed. His watch continues ticking at the normal rate. But the light carrying information about his actions to you stretches due to the intense gravity, delaying the information's arrival and compounding the visual slowdown. As the star approaches the critical boundary ever more closely, these effects intensify. The observer appears to move slower and slower from your viewpoint. His light becomes progressively redder and dimmer. The effect intensifies until something seemingly impossible happens. As the star reaches the Schwarzschild radius, the observer's motion appears to stop entirely from your perspective. He appears frozen in place, like a photograph. His image becomes locked at the boundary, suspended at that critical position forever. From your viewpoint, he remains perpetually falling but eternally approaching that boundary without crossing it. Time appears to have stopped for him, at least from your external vantage point. His light has become so extremely redshifted that it becomes virtually invisible. He appears frozen at the edge of this collapsed object, perpetually trapped there for eternity. This is why some physicists called such objects frozen stars. From outside, everything appears frozen at the boundary. From an external perspective, this boundary appears impenetrable. Nothing can ever cross it. Everything merely slows down and freezes at that boundary position. But here emerges the truly mind-bending aspect of this situation. What does the falling observer actually experience? Remarkably, nothing unusual whatsoever. From his own perspective, nothing indicates anything is amiss. Time continues flowing normally for him. He doesn't experience any slowdown. He doesn't observe anything strange. The critical boundary, the Schwarzschild radius, passes smoothly beneath him as he continues falling. There's no warning, no dramatic sign, no sudden jolt or discontinuity in his experience. From his perspective, it takes perhaps only a few seconds or a minute, finite time in his reference frame, to cross the boundary. He passes through this crucial threshold without even noticing anything different. However, once he has crossed this boundary, his situation has fundamentally changed. He attempts to send signals outward, radio transmissions, light beams, anything. But nothing works. Not because some barrier blocks the signals, but because space itself has curved so dramatically near the collapsed star that every possible direction points inward. There is no outward direction anymore. All possible trajectories, all conceivable paths through space lead deeper into the object toward its center. He has become trapped. Communication with the outside universe becomes impossible. Escape is physically impossible. As he continues falling from his own perspective, he experiences increasingly strong tidal forces, the gradual stretching and compressing of objects by differential gravity. Eventually, these tidal forces grow to infinite strength, crushing everything. The mathematics breaks down at this point, and we can only speculate about what actually occurs at the deepest center. So we have a situation where two descriptions are simultaneously true, yet they describe different experiences. From the outside observer's perspective, the falling observer remains frozen forever at the boundary. From the falling observer's perspective, he falls through the boundary in finite time and continues toward an inevitable doom. Both descriptions accurately represent the physical reality because time itself flows at different rates depending on gravitational strength. Near intense gravity, time runs slower relative to distant observers. At the Schwarzschild radius itself, from an external observer's perspective, time essentially stops. This might sound like pure science fiction, but it represents actual physics. Time genuinely does flow at different rates in different gravitational fields. We have measured this phenomenon directly. Your head ages faster than your feet constantly. Not dramatically, but measurably so. Your head is slightly farther from Earth's center than your feet. Gravity is slightly weaker at your head, so time runs marginally faster there. Over your entire lifetime, your head ages approximately 90 billionths of a second more than your feet. You cannot feel this difference, but it is absolutely real. In 1960, physicists conducted a beautiful experiment called the Moosebauer experiment. Researchers took a single photon, a quantum of light, and dropped it 24 meters from a tower's top to its bottom. They measured the photon's frequency upon arrival. The frequency had changed, shifted measurably. The photon had fallen from a region where time runs slightly faster to a region where time runs slightly slower, and this affected its frequency. The shift was incredibly tiny, roughly 1 part in 1,000 trillion, yet physicists measured it with precision. This definitively proved that time genuinely does flow at different rates in different gravitational environments. Near a neutron star, these effects become much more dramatic. Time at a neutron star's surface runs at roughly half the speed of time far away. An hour spent at the neutron star's surface corresponds to approximately 2 hours for distant observers. Near the Schwarzschild radius of a collapsed star, time, from a distant observer's perspective, becomes even more dramatically affected. An hour experienced by the falling observer might correspond to billions of years, technically infinity, for distant observers. This explains why the falling observer appears frozen to external observers, not because he is actually frozen from his own perspective, but because time runs so differently for him that from your distant position he appears to have stopped moving. Consider another measurement of this effect. Earth's core is younger than Earth's surface by approximately 2 days. This occurs because time runs more slowly deep within Earth due to stronger gravitational effects. Accumulated over 4 billion years since Earth's formation, this effect totals about 2 days. This is not speculation or theoretical possibility. The Moosebauer experiment measured it. Multiple other experiments have confirmed it. It's as real as any measured physical phenomenon. If collapsed stars exist, how would we detect them? By definition, they don't emit light. Light cannot escape from beneath the Schwarzschild radius. They represent invisible dark holes in space, locations where stars once existed but have now vanished into darkness. I considered this detection problem carefully, recognizing both its difficulty and importance. Several indirect methods exist for detecting these objects, though all are challenging. The first method involves binary star systems. Most stars don't exist in isolation. They have companion stars, and together they orbit their shared center of mass. If one star in such a pair collapses and becomes a collapsed star, you'd observe something distinctive. A visible star would appear to orbit empty space. But space isn't truly empty. The visible star is being pulled by something massive, something invisible. By carefully observing the visible star's motion, plotting its orbit, and calculating orbital mechanics, you could determine how massive the unseen companion must be. If this calculated mass exceeds the Chandrasekhar limit, if the object is too massive to be a neutron star, and if the object is dark, not emitting light, you might have detected a collapsed star. This represents one of the most promising detection methods because many stars exist in binary systems, and if collapsed stars are common, statistically, some should have visible companions whose orbital behavior would reveal their presence through gravitational effects. The second detection method involves gravitational lensing. Light bends when passing near massive objects. Einstein predicted this phenomenon in 1915 from his general relativity theory. We confirmed this prediction during the 1919 solar eclipse by observing starlight bending around the sun. A collapsed star would bend light even more dramatically than the sun. If light from a distant star passes near a collapsed star, the light's path curves significantly. The collapsed star acts as a gravitational lens. With perfect alignment, the collapsed star positioned directly in front of the background star, an observer would see the distant star's light bent around the collapsed object. The light might appear distorted, creating multiple images or form a ring of light. The probability of such precise alignment is genuinely small. The collapsed star, background star, and your telescope must align with exact precision. The odds are terrible, but not impossible. It remains highly improbable, but theoretically possible. If we observe enough stars and take sufficient photographs, eventually chance might provide the necessary alignment, and we could witness gravitational lensing around a collapsed star. In the 1960s, some colleagues held theoretical views about collapsed stars that I found unsatisfying. One widespread theory proposed that stars simply cannot collapse below the Schwarzschild radius. According to this view, some physical mechanism must prevent such extreme collapse. The argument proceeded as follows. If a star exceeds the Chandrasekhar limit, it must do something to avoid complete collapse. It must explode in a supernova, shed mass, anything to stay below the mass limit. Otherwise, if nothing prevented it, the star would continue collapsing past the Schwarzschild radius. Nobody wanted to contemplate what lay beyond that boundary, so this theory declared it couldn't happen. This explanation bothered me significantly because it doesn't actually explain why stars explode. It merely asserts that they explode because they must avoid collapse. That constitutes circular reasoning.